Please make sure you have your lesson, the blank lesson printed so you can take notes as necessary. Thank you. We are going to start this chapter 8 with some review concepts, and these are reviews from previous knowledge, some of them from integrated math 2 and some of them from previous classes all the way back to 7th grade. I believe the Pythagorean theorem was taught first in 7th grade, so let's go ahead and look at this. It says in a right triangle, the square of the length of the hypotenuse equals the sum of the squares of the length of the legs. So the first thing we want to do is we want to talk about the right triangle. The longest side in the right triangle is going to be our hypotenuse, always opposite the right angle. The other two sides are both of them called legs. If they are not equal to one another, one is a shorter leg, the other one is the longer leg. In some scenarios, the two legs are equal to each other, so then they can be represented by the same letter for both of the legs. And as an equation format, you can write the Pythagorean theorem as c squared equals a squared plus b squared, or a squared plus b squared equals c squared, which is using the symmetric property from geometry. So here's an example for you. So in the example, we have the length of the side A is 5, so let's substitute 5 for A. So 5 to the second part plus the length of the side of B is unknown, so I'm going to leave it as B squared. And the side length C is equal to 13, so that's going to be 13 squared. So in this scenario, we want to find the length of side B. So 25 is 5 squared plus B squared equals 13 squared is 169. And to isolate B squared, we subtract 25 from both sides. So we are going to get b squared equals 144. And lastly, we are going to take the square root of both sides. So b is going to equal to 12. So the length of side B is going to be 12 units. And in this case, we are talking about a Pythagorean triple, because each of the numbers of the side lengths are whole numbers. So 5, 12, 13 is called a Pythagorean triple. In slide 2, we are going to talk about special right triangles, which I believe you have seen in integrated math 2. The first special right triangle is the 45, 45, 90 right triangle. And then the second one is going to be the 30, 60, 90 right triangle. So I'm going to start writing them into the triangles, the angle measures. And then this one here is 60, 30, and 90. So that's why we named them those triangles. So if you're looking at your first triangle, which is your 45, 45, 90 triangle, you know that since you have equal angles for the acute angles, that means the sides opposite to them, then the side opposite to this one are going to have an equal length. So this is going to be an isosceles triangle with two equal legs, and then your hypotenuse is going to be square root 2 times either side A or side B, since those are both equal to one another. So in our scenario here, in the example, we have side C is given to us. So side C is going to be 8. So I'm going to use the equation here for side C. So C equals the 8 times the square root of 2. So I am going to substitute 8 for the side C, 8 times the square root of 2. To solve for A, we are going to divide both sides by the square root of 2, and we get a equals 8 divided by the square root of 2. As you remember, we don't like to leave the denominator to be a square root, so we rationalize the denominator by multiplying by square root 2 over square root 2. So a is going to be 8 times the square root of 2 divided by the square root of 4. So a is going to be 8 root 2 divided by the square root of 4, which is 2. So finally, if we simplify, we are going to get 4 times the square root of 2 is going to be side A. And since side A equals side B is also going to have a length of 4 times the square root of 2. So I'm going to box in all my answers for both of those sides. So now if I'm looking at the second triangle, which is the 30, 60, 90 right triangle, the relationships here are the longer leg, which is side B, is going to equal to the shorter legs times the square root 3, and the hypotenuse, which is side C, will equal to twice the length of the shorter side. So if I'm going to give you an example where I gave you the hypotenuse, which is C equals 12, so let's find first C equals 2 times A. So I substitute 12 equals 2 times A, and if I divide everything by both sides by 2, I'm going to have A equals 6. Now that I have the shorter leg, I can find the length of the longer leg. So B is going to equal to A times the square root of 3. Since my A was 6, B is going to be 6 times the square root of 3. So here is how we use the special right triangles. On the third slide, we have the trigonometric ratios that you learn from Integrated Math 2. And many of you probably heard of the szokkaktól, which refers to sine of an angle is opposite over hypotenuse. The cosine of an angle is adjacent over hypotenuse, and the tangent of an angle is opposite over adjacent. So now we want to talk about what we mean by opposite and adjacent. So if I'm talking about angle A, the side opposite to angle A is side A, which is the opposite leg to angle A. And if I'm again talking about angle A, side B is the adjacent side, which is part of the angle. It's one of the sides of the angle. If I were to look at another angle in this same triangle, like I'm looking at angle B, in relationship to angle B, the side opposite to it is side B, and the side adjacent to angle B is the side A. So it's always important when you are deciding what's the adjacent and opposite side, which acute angle is it in relationship to? Is it A or is it angle B? So let's look at this problem here. So the sine of A, which is this angle right here, is going to be opposite over hypotenuse. So the side opposite has a length of 13 and the hypotenuse has a length of 17. Then the cosine of the angle is adjacent over hypotenuse. So the adjacent side to A is 2 times the square root of 30 divided by the hypotenuse, which is 17. And the tangent is opposite over adjacent. So the side opposite to angle A is 13. And then we have to divide it by the adjacent side, which is 2 times the square root of 30. However, again, you remember that we can't leave a radical in the denominator, so we are going to multiply by the square root of 30 over the square root of 30. So this will simplify to 13 times the square root of 30 divided by 2 times 30, because the square root 30 times square root 30, if you take the square root, is 30. So then it simplifies to 13 times the square root of 30 over 60. And in this case, you are not able to reduce the fraction anymore. Now let us try to do the sine of angle B also. So the sine of angle B is going to be the side opposite to angle B, which is 2 times the square root of 30 divided by the hypotenuse, which is 17. The cosine of angle B is, again, the angle B is here, the side adjacent is 13. So we can say that's 13 over 17. And then let us look at our tangent. So the tangent of angle B is going to be opposite divided by adjacent. So the tangent is going to be 2 times the square root of 30 divided by 13. And in this case, since my radical is already in the numerator, I don't even have to simplify. So these were just some examples of our review topics, and I am going to post some assignments for you on Google Classroom to work on these. See you at the next lesson, which will be lesson 8.1.